So I'm not sure if I want to review what I just said, what I said last time, but roughly speaking, okay, so day 3, I guess more on the contact category. Okay, so if you recall from last time, to a surface sigma, we assign something called the contact category. Right, so this is the contact. And then, briefly speaking, the objects are dividing curves. Right, these are embedded one manifolds on the surface, which divide the thing, divide surface sigma into alternating positive and negative regions. So dividing curves gamma on sigma. And then the morphisms, let's say from gamma to gamma prime, are just contact structures, right, with the prescribed dividing set. So that was the contact category. There are some other variants. There was sigma comma f, where you put a bunch of points on the boundary. And then there was a slightly more complicated, I shouldn't have written this right there. Okay, maybe it's that. And then C of sigma could be written as sort of disjoint union of a bunch of connected components, which will write C of, C of sigma comma n. So n was basically this Euler class, right, which evaluated the Euler characteristic of the positive region minus the Euler characteristic of the negative region. So you have this sort of decomposition, and over each connected component, you have this universal cover. So you have C tilde of sigma comma n. This is the universal cover of the contact category C of sigma comma n. And one of the things you needed to do when you construct the universal cover is pick some sort of base point. So you actually needed to pick the base point gamma naught. Okay. So we did this kind of construction. Okay. And the first thing that we sort of want to understand, when you have a category, and then, there are also triangles. The triangles you get look roughly like this. This is a local picture. And you have a bypass exact triangle. Whenever you have something that looks like this locally, the red are dividing curves, you do this sort of sequence of operations. And in the contact category, if you go once around, you go back to the same thing. In the universal cover, you actually have this shift functor which drops your homotopy class by 1. Okay, so at the very end of the last lecture, I started talking about the Grothendieck group. So the Grothendieck group of a category with category C with distinguished triangles is basically just the free abelian group, the free Z module generated by the objects. You have ob of C, okay, and then quotiented out by relations. If you have a triangle that looks like something A, B, C, and then sort of you have something before and you have something after, you have this shift functor which drops your thing down like this. So if you look anywhere, so let's look here. Right, if you have 3 things in a row, you say B equals A plus C. So not A equals. Then you say B equals A plus C. Okay. Is that good? So completely abstract, but nevertheless somewhat useful. And I guess the other thing, I have to warn you that today there will be sort of absolutely no proofs, and then there'll be a bunch of statements that are made. So it'll become more and more incomprehensible as we sort of go towards the end.
Just like the velocity of things, is an invariant of a category? Is that?
Yes, that's an invariant.
Easier to understand than the category itself.
This one is actually usually much easier than the category. As you will sort of, the contact category by itself, you'll have like absolutely no idea of what sort of, how it's sort of, if you sort of think in terms of even sort of the graph, right? You have dots and arrows between them, and you try to visualize what does it look like. It's pretty complicated, right? Even if you don't know anything about contact structure, you can probably imagine you have a bunch of arrows and they're sort of complicated network of paths. But the Grothendieck group is already something linear, right? Which makes things a lot simpler. There are other invariants that you can try to extract, such as the Hochschild homology of the category and so on, but that's perhaps not really well understood at this point. Okay, so the first theorem is the computation of this Grothendieck group. The notation is usually K0 of something. So if you look at K0 of C sigma F, and for simplicity, you can actually calculate it for any kind of configuration. But for simplicity, let's assume that the boundary of sigma is connected. You have a surface which is connected, and then you have two dividing curves on the two dots on the boundary. Okay, so this is sort of in some sense, the simplest kind of situation you can get. And there was something else I probably wanted to assume. Well, maybe it's okay. So the first theorem is that this is actually isomorphic to the exterior algebra of the first homology of the surface with Z mod 2 coefficients. No, I guess Z mod 2 I'll denote as F sub 2.
This is not C tilde, this is C.
C, yeah. And if you sort of remember that the contact category actually is a disjoint union of a bunch of components. So you can actually sort of break this up into a bunch of components. And you have wedge 0 of H. I'll be a little bit lazy. For the moment, I'll write H equals H1 of sigma with F2 coefficients. And you have plus wedge 1 of H plus dot 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 plus wedge 2G of H. So that's as far as you're going to get with H1. Okay. And I think, so maybe the best way to sort of write, I'm not sure if I want to write, okay, so if you write K of sigma F, and then you put the integer n, right? So if you sort of indicate which connected component, it actually turns out to be wedge of, I don't really remember this, G minus n over 2 times of H. So all this is saying is that when n actually goes from minus 2g to 2g. So this is like n equals minus 2g, and then this is n equals minus 2g plus 2, and dot dot dot, and then you eventually get to n equals 2g. Okay. So that's the kind of correspondence that you get.
Is there a multiplication defined on this? I mean, you said it was the exterior algebra. You just
okay, so there is actually, but I won't say anything about it. You can actually sort of promote it into a Grothendieck ring, but okay. The second thing is that if you're interested in this sort of universal cover version, K0 of C tilde of, okay, so what is it? Sigma, comma, F, comma, n, comma, you pick some sort of dividing set in this connected component, then this is actually isomorphic to something a little bit more complicated, which is some index times H1 of sigma with some sort of strange coefficient ring. Okay. It's sort of scary looking, but Z bracket H is the group ring. So here H is not that. H is actually H1 of sigma, now with Z coefficients. Okay? And then Z bracket H is the group ring over H. Okay. So it actually, if you do more work and do this universal cover version, you actually get substantially more information. Okay. So previously, you were just doing, stuff on like the first homology of sigma with Z2 coefficients. Now you're doing the first homology of sigma with some crazy group ring coefficients. Okay. Is that okay so far? Maybe it's not so clear what's happening, but
can you provide the generator of these
generators of
these each degrees?
Yeah. Okay. So maybe I'll give you a sort of a slightly more specific example where I can actually provide you the generators. Okay. So.
So you said you want proof because is the proof contact topology or algebra?
How do you prove this?
I mean, is it contact? Is it like something about are you using bypasses and?
This is okay. So I didn't really want to say anything about the proof. The proof.
Asking whether it's a contact topology or algebra. The statement.
I don't want to know.
Is this statement?
Proof it. I just want to know: is it contact topological proof, or is it just?
I'm not sure how you say.
Never mind. Go ahead. Just you.
No, it's actually sort of neither. So maybe I'll do, since there's some demand for some sort of explanation. You have sigma. Let's say sigma is a disk with n points removed, minus n holes. Okay. So in this case, you have something that looks like this. A disk with n holes. Then let's consider the following kind of sort of dividing set. So let's say, I'm not going to tell you what n is, but n is automatically determined by the gamma that you give, right? So I will be sort of interested in C tilde of sigma comma. Let's just say this is the gamma. Let's say gamma. I'll call it gamma 1. So let's say some sort of gamma 0. Let's call this gamma 0. Okay. Then it turns out that the Grothendieck group, K0 of C tilde, I'll be lazy and I'll just write C tilde for now, right? Is actually, in this case, it's actually neither of these because the number of points on the boundary is different. But let me just, you have to believe me, but that this is actually Z bracket H, right? H is again the first homology. It's Z bracket H1 of this sort of disk sigma with Z coefficients, and then you sort of take the direct sum n minus 1 times. You actually do n minus 1 times. You have Z bracket H1 sigma Z. And what are the generators of this? It actually turns out that this is the first one, and then the second one, 2, 3, 4. You take, you pick sort of any two successive ones and draw a circle around it. So I draw a circle like this. This is the second generator, right? And if you only have 4 holes, oops, 1, 2, 3, 4, and this is the third generator. So you have gamma 0, gamma 1, gamma 2, and then these are generated by gamma, in this case, gamma 0, gamma 1, gamma 2. So you just take any two dots in succession, and you draw a curve around it, and then you have something. Okay. So that turns out to be the Grothendieck group of this, this category. Is this sort of slightly okay? Maybe not completely clear, but that's the... And that example is a little bit slightly important because I would like to talk a little bit about, for example, braid group actions on things like this.
So these scenarios all the dividing set?
If you think in terms of the Grothendieck group, right? Any dividing curve, right? So the question is like, given any dividing curve, can you write it as a sum of like things like this after sort of attaching? If you attach a bypass, and right, this one is the same as the other two, right? So can you actually write something like this in terms of the other, like in terms of some of these things? And roughly speaking, the idea is so. The question is, the real question is that whether there are actually more relations than you would like. But sort of roughly speaking, for example, right, if I have something that looks like this, and I have some dividing set which actually intersects like many times, right? Is that okay? So locally you have something that intersects many times. All you have to do is take this arc, right? Then what do you see? So you see that if you resolve once, it looks like this. If you resolve the other way, it looks like this, right? And the important thing is that you notice that the intersection with a number of, this procedure actually decreases the number of intersections with a particular arc. So you can sort of do this inductively and start reducing the number of intersections with various things that you have on the surface and get it into this form. Okay. Is that sort of convincing? Right. The question is that, like, so now you know that typically it's not so hard to show that these generators actually generate the Grothendieck group. But it's actually sort of tricky to show that these are all there are no other relations. And that's sort of, yeah. Sort of.
So describe the trivial curve. Trivial curve.
Trivial? I don't understand what you mean by the.
No trivial curves over there.
If you have a trivial, if you have a homotopically trivial curve,
then
that's a zero. That's a zero in the Grothendieck group. Yeah.
Over-twisted one.
Yeah, something that corresponds to an over-twisted one is zero in the Grothendieck group. Okay, so next we discuss mapping class group actions. Unfortunately, this is a little bit trickier. Mapping class group actions. Or mapping class group representations. So the first thing, the setting which is easier is that the mapping class group map sigma boundary sigma. These are the diffeomorphisms of sigma that are identity on the boundary. Okay, this clearly acts on the category, let's say C of. Okay, I'll just be lazy and just write C of sigma. Okay, so I need to have boundary, so okay, C of sigma f. Okay. So what does this mean? So, right, suppose I have gamma. Right, suppose I have a morphism. Right, I have two objects, two dividing curves, gamma and gamma prime, and then I have a contact structure with dividing set gamma here and then gamma prime on the other side. Okay, so if I have so now I get a little bit into tricky territory. So from now on, I'm going to make no distinction between dividing curves and isotopy classes of dividing curves. Okay, so what this, right? There's some sort of functor that should take this package, and it's sort of clear, right? If you take phi in the mapping class group, right, it induces sort of a map that takes you to. Right. So basically everything in sight is acted on by phi. Right. So the dividing curve gets acted, and then, right, and then the contact structure gets acted on by phi. So this is pretty straightforward. Right. Like given a dividing curve, basically given a curve, you can send it to phi of gamma, right? And then given a contact structure, that's also sort of you can send it to phi of it. Okay, so there's a completely natural action on the category, and then, well, what does it descend to? Right? So if you have an action on a category, typically you expect this action on a category to descend to a linear representation on the Grothendieck group. Okay, so it actually descends to a representation. Right, let's call it rho from K0. Oh, sorry, not K0, from the mapping class group of sigma, of boundary sigma, to, well, GL of the Grothendieck group. GL of the Grothendieck group of C of sigma F. Well, but what is this, right? This we knew in this sort of in the contact category. This was just the exterior algebra of H1 of sigma, right? And what's probably the only reasonable natural action that you can have on the exterior algebra of sigma with like F coefficients? Well, this is just the homological representation. This is just the standard. This is. Oh, maybe I'm not. This is the usual homological representation. The mapping class group acting on the homology of. And if you have exterior algebra, like exterior algebra is just sort of, go from the usual representation to the exterior algebra one, exterior power version. Okay, so now things get a little bit more complicated. You may not like this, but sort of bear with me a little bit. So the mapping class group acts on this category like this. How does it act on the universal cover? Right? So it's sort of a little trickier. Let me just write the universal cover as something like C naught, C tilde of gamma naught, to just indicate the base point. Okay, this is actually trickier. And why? So what's something in here? You have gamma naught to gamma, right? And then you have some sort of homotopy class of two-plane fields. Right? This is an object, right? An object in this category is some homotopy class of two-plane fields from the base point to the object that you're interested in. Okay? And then, well, oops, not psi, phi. Right? So what does it do? Well, it sends it to, what does it naturally send it to? It'll send it to phi of gamma naught to phi of gamma. Right? This is exactly what we were writing. So phi lower star zeta. Right? Okay. Is that okay? So this is a completely natural thing. So if you have your phi, it'll just act on the whole surface and it sort of just, act on it exactly as you would expect. Well, but there's sort of a problem. This is C of, right? These are elements in C tilde of gamma naught, right? But then you have some things which are actually no longer in C tilde of gamma naught. It's actually in C tilde of phi of gamma naught, right? So maybe I'll call this phi lower stars. Okay. Is this so far so good? Right. And then, well, okay, so there's some sort of issue, and I would like to compare something, right, in C tilde of gamma naught to C tilde of gamma naught. So what you do is find a collection. This is where it starts getting a little bit non-canonical. So you actually choose a collection of paths. So choose a collection of paths, right? So i.e. for each. Oops, not if. For each phi, right, you pick some sort of path from gamma naught to phi of gamma naught. So you call it, I don't know, do I want to give it a name? Zeta sub phi or something. So this is, again, this sort of question about like fundamental groups, right? You have fundamental groups and you have like different base points and you want to relate the base, like the two different fundamental groups. So usually you have to actually sort of add an extra arc from a path from the one you're interested in to the one, or this is the one you're interested in and the one you have. Okay. So now you compose and you get gamma naught to phi of gamma naught to phi of gamma. Okay. And this is, what is this? This is zeta sub phi, and this is phi lower star zeta. Okay. Maybe the sort of notation is very misleading looking, complicated looking, but anyways, you compose. Okay.
Is it easy to see there is zeta phi?
Yeah. So we were sort of discussing this about sort of connected components, right? So if you believe that each of these, right, the C of sigma Fn is actually connected, then you actually do have a path. So you have to believe me. There was some sort of discussion last time about the thing I was claiming were the connected components actually being connected components.
No, but the action of phi, right? Is it obvious to see the action of?
Yeah, the phi actually keeps the n. It actually does not change the n. Because remember, we were just talking about the Euler characteristic of the positive region minus the Euler characteristic of the negative region. So no matter what you do by phi, the positive region will have the same Euler characteristic, and the negative one will still have the same Euler characteristic. Okay, so you do this sort of procedure. Okay, and at the end of the day, I will maybe spare you some details. So that what you get is something horrible sounding. So the fact is that the action of the mapping class group, sigma boundary sigma, okay, on C tilde gamma naught, descends to a projective crossed homomorphism. So a projective crossed homomorphism. So map of sigma boundary sigma to what is it? GL of K0 of C tilde gamma naught. Okay, so what's this projective business? So let's sort of look over here. You had the map phi lower star, and then you had this sort of strange thing which was sort of dependent on the choice, right? And then let's just think of what do I want to call phi? Yeah. So the point is that you had some sort of choices here, right? Suppose you made different choices, what happens, right? All you're doing is you have some sort of category here, and at the tail end, you're picking which path you want to choose. And if you sort of look at what's the difference, right? If you look at the difference of two paths, right? Then what? You have like basically gamma naught and phi of gamma naught. And I have one path and I have another path, right? Remember that we were saying that what's the difference between sort of two contact structures with the same endpoints, right? That consisted of an element in Z plus H1 of the surface, right? There was some sort of difference that we could sort of measure. Okay. And what we want to do is actually write this more or less. The Z corresponded to something like plus or minus 1, right? There was some sort of Hopf invariant that was. Right? So when you go around the triangle and you look at the Grothendieck group, that sort of created the plus or minus 1. And then H1 of sigma, right, that difference is actually if you write it in terms of the group ring now has h1 of sigma coefficient, like z bracket h1 of sigma coefficients. But so if you write it multiplicatively, the difference between sort of two choices results in a unit of z bracket whatever. So it's a little bit hard to say. But anyway, so if you have the difference in choices, difference in choice of path results in so how do you say it? A difference in change. Maybe I'll just write this sort of more carefully. So okay. So each phi in map sigma boundary sigma, okay, gives rise to a z bracket h, right? This was the coefficient system. So z bracket h linear isomorphism. Okay. I'll write it as phi lower star from k0 of c tilde gamma naught to k0 of c tilde gamma naught. Okay. So if you sort of look at this map, okay, this descends to the k group level. So that means you have the linear map from here to there. Right? Remember the coefficient ring of this was actually z bracket h. It's actually z bracket h linear. Okay. And yeah.
Can you tell us what the z bracket h module structure on the k0 group was?
So last time I said something about, remember if you actually, okay. So an element in C tilde was a homotopy class of paths from gamma naught to gamma, right? And if you change the and the difference between two homotopy, so the difference between two plane fields, right, is given by this sort of z plus h1 of whatever, right? h1 of sigma. And so if you think of h1 of sigma multiplicatively, then that's the z bracket h thing. Is that okay? So if I add a z bracket h thing, then I'll change the homotopy class by a certain amount. Wake up, Andras.
You didn't go to acting yesterday.
Okay, so and the point is that this phi lower star is unique. So phi lower star is well defined up to a choice of unit, up to units in the group ring z bracket h. Okay. So whenever you have some sort of representation, if you write down a matrix, the matrix is not completely determined. It's determined up to multiplying some unit like in front of it. Okay. And this is usually called a projective representation. So if you sort of if it's well defined up to multiplying by something in front, then well it's almost determined but maybe not quite.
Okay. It's like a mapping PGL.
Yeah, yes, that's right. Maybe I should have written it as PGL, but I guess the P would have been a little bit not so clear. Okay, and then the second issue is what is a cross homomorphism? So suppose you have two groups. So given two groups, G and G prime are two groups, and G acts on G prime. Okay. Then a cross homomorphism is really something that's slightly more general than a homomorphism. It's given by a map from G to G prime such that eta of A times B is not quite eta of A times eta of B, but eta of A times you have eta of B, and then you have some annoying factor here, which is A acting on eta of B. So you have eta of B, and then G acts on G prime, so A acts on this thing, and then you multiply by eta of A. This is some strange generalization of homomorphism. But it sort of turns out this category, when you drop it down to the sort of mapping class group level, is exactly has this kind of transformation property. Okay. Sometimes it turns out that the cross homomorphism, this action of G on G prime, is actually trivial. So sometimes, well, yeah, sometimes it just happens that it's sort of trivial, in which case it just becomes a homomorphism. Okay. Are there any questions? I'm not sure if you're understanding anything anymore, but.
Well, in other contexts, does cross naturally go with projective?
Yeah. What? No.
Cross and projective usually go together.
They don't usually go together. Okay, but you actually have cross homomorphisms which show up quite frequently in sort of representations of mapping class groups. So it turns out, you may or may not know, but if you open up Biermann's book and you sort of start looking at all sort of the list of various representations, you'll find things called the Gassner representation. There's also the Burrell representation, and also this other thing called the Magnus representation. There's several representations of mapping class groups and braid groups, but it sort of turns out that sometimes for example, the Gassner representation is supposed to be a representation on what's called the pure braid group, the braid group where you sort of actually fix the points. But if you actually want to think of the Gassner representation as a representation on the whole braid group, you actually get what's called a crossed homomorphism. So I don't know if you know this, like there's so many people who like it's sort of classical mathematics, and you may not have heard about these things. But if you sort of think, right, so once again, if you want to think of action of the braid group on some sort of vector space, right, then sometimes the representation, like the way it's sort of treated in various texts, you sort of restrict a smaller sort of subgroup. On the smaller subgroup, it's actually a genuine representation, but you can extend it to a larger group on which you have a crossed homomorphism. Okay, so the reason I'm saying is that this actually does show up. So the example of this. Suppose we have sigma with the exact same example that we had, D2 minus a bunch of points and holes. Okay? And then we were interested in things that look like, the category that look like this. Okay. So the statement, so theorem, so basically due to my student, she basically did it for the corollary, but if you reinterpret this properly, you get the following statement. So the action of the braid group Bn on Cn of sort of C tilde of gamma naught, so it's this subcategory, okay, descends to what's called the reduced Gassner representation. So reduced Gassner representation of the braid group. Okay. So maybe I won't actually define what the Gassner representation is, but remark is that the Gassner representation representation is actually a representation on when restricted to the pure braid group. So when restricted pure braid group, I don't know, sometimes it's denoted P sub n, and if so if you don't remember what the pure braid group is, it's the braid group that's a subset of the braids where you what is it? How do you say it? You actually fix the points point-wise. So here, so for example, in the braid group, you can do this half twist where you're actually permuting the points, but in the pure braid group, you're actually requiring that the endpoints actually, the initial point and the terminal point are the same.
Homologically trivial ones, right? Homologically trivial ones.
Yes. Or another way of saying this is that you have a homomorphism to Sn, and it's the kernel of the map to Sn. Okay. So
do you have any canonical choice of base point gamma 0?
No. That's the really weird thing. There's no canonical choice, as far as I know.
Even in that case?
Even in this case, I don't know. I usually do this calculation assuming this is the base point, but I don't. So so there's actually this sort of up to units issue that's always there, but apart from that, if you chose a different base point, then the representation that you get is the same as the previous one up to unit. So there's something a little bit unsatisfactory, but
To me, if you take the largest boundary circle in the picturesque gamma 0, then it is fixed by any interaction.
Which one are you talking about?
The boundary. Almost boundary.
You're taking a circle like this?
Can I use it?
No, it has the wrong Euler class. So the way you calculate this is you take chi of r plus, sort of these things are given signs. You take chi of r plus minus chi of r minus. So you need, I'm interested in the subcategory where the chi is actually the one that's given by this. Yeah, so somehow, if you did the stuff you're suggesting, then you're actually in a different component.
In particular, this Gassner representation acts on some exterior algebra of H1.
No, the Gassner representation, C tilde of gamma naught, where gamma naught is actually this. So the classical Gassner representation is actually something that it doesn't act on the exterior algebra. It actually acts on the lambda 0 of wedge 0 of the exterior algebra. So it's actually, this one refers to somehow the furthest right non-trivial portion of the K group. So presumably the other ones will be related to something about exterior representations of the thing, but the calculation has not been done. So
lambda 0 then is just the grouping itself? Lambda 0
now is like however many copies of the group ring, the number of the rank is given by H0 of the surface, H1 of the surface. So remember, like we were saying, there's actually something a little bit tricky about this, but just sort of believe for the moment that this category, the K group of this category is generated is free, right? It's a free Z bracket H module, right? And it's generated by 3 elements, 1, 2, I guess in this case 4. This sort of, if you have n holes, it's generated by n minus 1 elements. Yeah, so it's sort of basically like the homological representation, except it has other things attached to it. Oh no, it's not the homological. It's the somehow reduced homology representation or something. So in some sense, you're. Okay, when restricted to the pure braid group, but then on the other hand, it's if you it's not commonly known, but you have to sort of be somewhat knowledgeable or affiliated with students of Morita. And if you ask students of Morita or read their papers, then you actually realize, you find out that the Gassner representation can actually be defined on the braid group. So it extends to a crossed homomorphism on the braid group. Okay, so maybe that's all I'm going to say about representations. Is that okay? Okay, so the next thing, is it part 2 or part 3? So we talked about mapping class groups, so maybe part 3. Let me just sort of quickly talk about the sutured floor homology functor. Maybe I should write sutured Heegard floor homology functor. Sutured Heegard floor homology functor. So how much time do I have? I have about 25 minutes. Is that right? Okay. So I'll just sort of blitz through some certain facts, sort of a collection. I'll just sort of state as if I haven't been just stating a collection of facts today. I'll just state a bunch of facts as well. Okay. So the first thing is, like, what is a sutured manifold? So a sutured manifold, sort of due to Gabai. So what is this? It's a compact, so a sutured manifold M gamma is a compact oriented 3 manifold. So a compact oriented 3 manifold M. So together with an embedded 1 manifold on the boundary of M. So with an embedded 1 manifold gamma on the boundary of M. Such that gamma divides the boundary of M into alternating positive and negative regions. Such that gamma divides boundary of M into alternating sort of positive and negative regions. Okay, so by now, if you know something about contact topology, this sounds suspiciously sort of familiar, right? So this is just the dividing set. Except that you're actually not specified the contact structure inside. Okay, so we have sequence of black boxes. The first one is that to a pair like this, you can assign sort of a variant of a Heegard floor homology group. So you might have heard about this. So to a pair M gamma, you can assign what's called the sutured Heegard floor homology group. Sutured Heegard floor homology group. Which is usually denoted SFH of M gamma. And this is defined by Juhas. So it's defined by Andras Juhas. Okay. So in some sense, if you're thinking in terms of thinking contact topologically, you have a sort of a three manifold with boundary, and then sort of waiting for contact structures to be sort of filled on the inside or something. Right? So you have some sort of receptacle that's waiting for contact structures. Okay. So that was Juhas. The second thing is suppose let's write like M gamma Xi for contact structure Xi for contact structure Xi on M with convex boundary and dividing set gamma on the boundary. Okay. So if we write something like this, then to such a contact structure, we can assign an element of the of the sutured Hegardt-Floer homology group. Okay. So we can assign an element C of let's say M gamma Xi, to an element. So there's an element inside SFH of minus M. Somehow, for some reason, you need to reverse the orientation, but let's not worry about this for the moment. Okay. And this generalizes the contact invariant as defined by Oshrat and Szabo in the absolute case. So which extends the contact invariant defined by Oshrat and Szabo in the closed case. Right. Oh, C means contact invariant of M gamma Xi. Okay, so far so good. And well, okay. So if maybe a couple of facts. If this is over twisted, if the contact structure is over twisted, the contact invariant is 0. And also, if you can embed this contact manifold into a Stein fillable contact manifold, then the invariant is non-zero also. So this sort of a couple of natural properties. Okay, and the third one, so I guess I should probably cite people because so this is myself and which one is which? Kazes and Matic. And then the next theorem is also ours. So suppose you have a contact manifold or sutured manifold be a sutured submanifold of M gamma. So by this I mean you have a sutured manifold. You have a manifold contained in the other one. So here you have a manifold M prime, right? And then on the boundary you have gamma prime. And then you have a larger manifold M, and then it has boundary gamma. Not boundary gamma, dividing set in the boundary gamma. Right? So this smaller one is M, and then the bigger one, M prime, and the bigger one is M. And then suppose I have a contact structure in between. Suppose I have a contact structure hanging out here. So Xi. Yeah, that was the definition. The definition was that you just have a submanifold M prime of M, right? And then I just put sutures gamma prime on the boundary of M prime, and then yeah. So so this is sort of a lazy definition. Okay. Then there exists and then I won't say anything about Xi, so I'll just write Xi here to mean it has the properties as you want. Okay. then there exists a natural map phi, which depends on psi, which takes you from sutured floor homology group of minus m minus gamma, oops, the other way, minus m prime minus gamma prime, to SFH of minus m minus gamma. Okay. So you have a map. If I'm given a xc, I have a map from the smaller one to the bigger one. Okay. And then in particular, if I have a contact structure zeta on here on the smaller piece, right, then the contact invariant of zeta gets mapped to the contact invariant of zeta union xc. Okay. It's sort of a natural procedure. Okay. Okay, so once we have this, you can actually write down a functor. Right, so all this whole thing is actually functorial. So that means, for example, this means that if M is a 3-manifold with boundary sigma, okay. Suppose I have a 3-manifold with boundary sigma, then there exists a functor which how do I want to write this? Let's say f sub m, which takes you from c tilde of let's say sigma comma some sort of reasonable dividing set, right, to the category of z modules, which sends gamma to, right, well, what's the only thing you can possibly send it? SFH of minus m minus gamma. Right, so suppose I'm given.
Tilde is the morphism that divided.
Yeah, it's a universal cover. So there's actually slight trickiness going on, but
Base
what?
Base when fixed.
Yeah, but let's sort of for the moment ignore. So for the most part, you can ignore the base point in this case. The only thing that sort of comes in is when you look at triangles. But so yeah, for the moment, let's just sort of ignore the fact that you have some sort of homotopy class here, right? Okay, and then suppose if you have a like c to gamma prime, right? Then you send it to, well, gamma prime gets sent to SFH of minus m minus gamma prime, right? So it'll start looking like a commutative diagram. So maybe I'm gonna. So I have this package. It gets sent here. Okay. So we have this, and then given the contact structure xc, you have this natural map. So you sort of, right? You have this. Good. So this. Anyways, this procedure gives you some sort of, given a 3-manifold, it gives you a functor from this contact category, or the universal cover of the contact category, to the category of Z modules. Okay. Okay, well.
So, can I ask a question?
Yes.
So then the sutured floor homology is the group which consists of context structures with boundary context structure fixed.
It's not quite. It's not quite. So remember the Heegard floor homology groups were defined by. You can sort of roughly think of them as like populated by contact invariants, but maybe a more correct way of thinking, sort of to do it more correctly, you need to write down the alpha curves and beta curves and so on. So that definition I'm not going to say anything about. But you can, for the moment, you can think of it as some sort of receptacle which has fields that that are sort of given by contact structures or something. Yeah.
how does the context structure points?
Give you something in the... Yeah, so to a context structure, so we've already discussed open book decompositions, right? Given an open book decomposition, you can usually write down a relatively canonical looking representative of the Heegard floor homology. And this canonically looking representative happens to be the contact invariant. So I won't, that's probably the only thing I'm going to say. Any other questions about black boxes? Okay. Okay, so we have this, but then on this side you have triangles, and you need triangles on this side, right? So
These are all for closed three manifolds.
no, these are like open. There's not open. The three manifolds with boundary.
Okay, so
You-
three manifolds with boundary, there might not be a manifold which has open book decomposition.
But there's a sort of a notion of a partial open book decomposition. You can actually define sort of open book decompositions which are adapted to a contact structure with this convex boundary. So there's such a notion. Right? This gets mapped under the functor to, well, SFH of minus m minus gamma 1 to SFH of minus m minus gamma 2 to SFH of minus m minus gamma 3 and so on, right? And so if this is exact, right, if you have a bypass triangle, then this side also is exact. And if you sort of do this correctly on this level, if you do this on C tilde, right, then as you sort of go around, you actually drop by 1, and this actually sort of has grading shift that goes down by 1. So it actually works perfectly.
It can be done for any knot. Any knot we can get the Suture blow homology.
It can be a knot, but it doesn't have to be a knot. You can,
Right.
yeah, you have something with boundary, you can get a. Yeah. So
Do you put a chain complex rather than homology group?
on the right hand side, is it a? Oh, is this? This is actually on the homology groups.
Only homology group.
Uh,
So the target is not the derived category of the module.
no.
But triangulated structure, you need some triangulated category this side.
You don't need it on the chain group. I don't know. I don't understand what's going on, but this is sort of more like the floor. This side is sort of similar to the floor exact triangle. Yeah, you don't need to go to the. Right, the triangle is sort of exact. It's actually right on the nose. So
you have.
you can still work on the chain level if you want, but I don't know. Yeah, I don't know. It doesn't seem like you get anything more by.
But it is not triangular category.
No. But
Category is
What do you do? Domain is honestly a triangulated category. C is honestly a triangulated category.
it's not. But you can basically sort of complete it into something that's more honestly triangulated. So. Yeah. Okay. So if you want, maybe let's replace it with the chain groups. There's no, from the perspective of the theorem, there's no difference. So.
So does this functor descends to the Grodan group?
Sure. Yeah.
So
I'm okay. So maybe I will. That's the next thing I was going to talk about. Right. So. If you already sort of think this is completely incomprehensible garbage, it'll become even more incomprehensible. But let's talk about what happens on the Grothendieck group level. Right. So how do you actually pass? If you have a functor like this, how do you actually pass to the Grothendieck group level? So this is usually called decategorification. And so to a gamma, you're sending, well, so previously you were sending it to SFH of minus m minus gamma, right? And then you want to take the Euler characteristic. So how do you take the Euler characteristic? So here I have to sort of mutter a couple of words. So in this, when you're computing sutured floor homology groups, you're doing basically Lagrangian intersection theory of two Lagrangians. And then to a Lagrangian, so if you have two Lagrangians, you have a reasonably canonical Z mod 2 grading, which is you orient two Lagrangians and say, well, it's positive if the intersection is positive, it's negative if it's negative, and so on. So this, you get some sort of canonical Z mod 2 grading. So exists. I'm not sure if it's, is it? Well, canonical if you orient the Lagrangians, but exists some sort of canonical Z mod 2 grading. And using this, you can sort of calculate the Euler characteristic. And so this is actually, by definition, the sum over spin C structures of M, or maybe relative spin C structures. I'll be sort of lazy. Of SFH of minus M, or sorry, the Euler characteristic of this M gamma S. Okay, and this is sort of calculated by using some sort of Z mod 2 grading. Okay, so it's, you sort of, okay, to a positive crossing, sort of positive intersection, you assign 1. To a negative intersection, you assign -1. And then you actually want something with values in the Grothendieck group, so with the coefficient group. So this is actually, so let's write it multiplicatively, e to the sort of s minus s naught. So you sort of pick a spin C structure, right? And then given S, you can sort of talk about the difference. And the difference in spin C structures is an element in H1 of sigma. Right, so this is actually an element of H1, not sigma, H1 of M. Okay. Right, so you have some, these are numbers, and you have sort of e to an element of H1 of M written multiplicatively. And the fact that you have some sort of exact triangle implies that you can actually sort of, if you descend to the Grothendieck level this way, it actually will sort of descend to the same thing on the Euler characteristic level. So okay, so the upshot is that you actually get some sort of TQFT-like, so you get TQFT. So 2 plus 1 dimensional TQFT-like map. Right. So for example, it's probably easier to sort of. So you have M, and suppose it has two boundary components, sigma 1 and sigma 2. Okay. Then you have it actually induces a map phi from the K group, K0 of C tilde of sigma 1 with some dividing set. Okay. Tensored with K0 of C tilde of sigma 2 with some sort of dividing set to this coefficient ring, which is, what is it? Z bracket H1 of M. Okay. So you have some sort of thing that looks very much like a TQFT. You have to sigma 1 you assign a vector space, which is this Grothendieck group, and then to sigma 2 you assign some sort of Grothendieck group, and then to sort of M you assign some sort of map which comes from the tensor product to that one. Okay, so I think I'm going to stop here.
Thank you. Are there questions, remarks?